These black holes are acting very strange. Should we be worried? Physicists relish encountering perplexing enigmas that don't immediately align with established theories. This unusual black hole provided just such a puzzle. Recent theoretical simulations propose that the peculiar characteristics of this scenario can be clarified by the presence of a third solitary black hole intruding on the binary system's final interactions, giving rise to a chaotic dance. An unusual event in 2019. In 2019, an extraordinary event transpired. NASA detected a gravitational wave signal from a black hole merger that broke records. It was the most massive and remote such event identified, emitting an exceptionally energetic signal that manifested more as a significant impact than the typical chirp. Adding to the intrigue, the resulting black hole from the merger was about 150 times the mass of our Sun, marking the first direct observation of an intermediate mass black hole. Adding to the oddity, the merging black holes were in an elliptical orbit, deviating from the usual circular path. Their axes of spin were also more significantly tilted than expected compared to their orbits. The collaborative detectors registered the telltale signature of a binary black hole merger, with brief wiggles lasting less than 1/10 of a second. The shorter the signal, the greater the mass of the merging black holes, 85 and 66 solar masses in this case. One solar mass equates to the mass of the Sun, approximately 333 times Earth's mass. These black holes combined to form a new, larger black hole around 142 solar masses, releasing energy equivalent to 8 solar masses during the process. This accounted for the robust signal captured by the detectors, the peculiarity of the event. What set this event apart was the measurement of 142 solar masses, positioning it squarely within a mass gap for black holes. Black holes typically fall into two categories: stellar mass black holes ranging from a few to tens of solar masses, and supermassive black holes found at the centers of galaxies, spanning from hundreds of thousands to billions of solar masses. The former forms from massive stars supernovae, while the latter's formation process remains largely mysterious. Another oddity was one of the progenitor black holes weighing in at 85 solar masses, which contradicts prevailing models of stellar evolution. Stars in the mass range of 65 to 135 solar masses would not go supernova, leading to black holes. Such stars would become unstable and shed much of their mass, eventually going supernova. However, this process would result in a black hole less than 65 solar masses. The hypothesis of a hierarchical merger. Physicists at the time proposed that this black hole was a product of a hierarchical merger, where the progenitor black holes themselves formed from an earlier merger before converging. This implies the presence of other black holes in the vicinity, allowing for multiple mergers. However, evidence was inconclusive, and physicists hoped to gain insights from corresponding electromagnetic data. The Zwicky Transient Facility, ZTF, detected a flare about 35 days after the gravitational wave signal from the same sky region. This was atypical, as black hole mergers typically don't emit light. One explanation could be that the merger didn't occur in empty space. A supermassive black hole encircled by a rotating gas disk can draw smaller black holes into the disk, enabling them to grow. Over time, these smaller black holes could form binary systems that eventually merge. The simulation's insights. In a simulation, it was shown that the presence of multiple black holes in a vast gaseous disk significantly raises the chances of collisions that result in larger black holes. This scenario also explains the elongated elliptical orbit of the merging black holes. If these black holes entered orbit within the disk, the material would absorb some of their motion's energy. Moreover, the gravitational pull of a third black hole outside the binary system could perturb the orbits, transforming them from circular to elliptical. This situation is analogous to the classic three-body problem, described humorously by co-author Hiromichi Tagawa of Tohoku University as a chaotic tango involving three black holes engaged in a dynamic dance. The simulation revealed that, in such circumstances, the probability of black hole mergers with eccentric orbits increases by a factor of 100. In these environments, the customary velocity, density, and spin axis of black holes are remarkably high. In this setting, smaller black holes exhibit motion akin to a colossal billiard game. Furthermore, The presence of wide circular binaries becomes improbable. This situation could also elucidate the peculiar spin axis of two binary black holes before their merger. Ordinarily, their spin axes would align in the same direction, approximately 90 degrees from their orbital plane. However, the two black holes displayed significantly elevated spin axes. According to the authors, a third solitary black hole's gravitational force could effectively exert influence on the binary pair. This influence would maintain their shared direction of spin while slightly altering the axis. Despite the intriguing explanation provided by simulations, it has yet to yield a conclusive resolution. For numerous years, researchers have been dedicated to comprehending the structure of such gas disks. However, this challenge remains intricate. Our findings are contingent upon the disk's flatness and the movement of black holes within it. Time will ascertain whether we acquire further insight into these disks as we amass a broader assortment of black hole mergers, encompassing more extraordinary instances like the ones described. According to scientific consensus, supermassive black holes, which boast millions to billions of times the mass of our Sun, reside at the cores of most galaxies. Astronomers yearn to unravel the origins of these colossal entities. While it's believed that the majority emerged through the merging of smaller supermassive black holes, conclusive observations were lacking. This situation might change due to a recent study. Observers studying a supermassive black hole have detected signs indicating a closely orbiting companion. This colossal duo, referred to as a binary, orbits each other every 2 years. If accurate, the binary's orbit diameter is 10 to 100 times smaller than the only other known supermassive binary. The impending merger of this pair is estimated to occur in around 10,000 years. Although this might appear as an extended period, it typically takes around 100 million years for supermassive black holes of this magnitude to commence orbiting each other and eventually converge. Hence, this binary is nearly 99% of the way towards collision. Notably, black holes do not emit light, but their gravitational influence can amass disks of hot gas around them, subsequently expelling some of this material into space. These jets can extend over millions of light years. A jet directed towards Earth appears notably brighter than one directed away, leading astronomers to term supermassive black holes with Earth-directed jets as blazars. A blazar named PKS, situated around 9 billion light-years away, features prominently in this recent research. Among a collection of 1,800 blazars, PKS demonstrates an unusual trait. Its brightness exhibits regular fluctuations akin to a clock's ticking. Researchers theorize that this rhythmic variation results from a second black hole's gravitational influence, as they orbit each other every 2 years. Each of these black holes is estimated to possess several 100 million times the mass of our Sun. To corroborate this discovery, scientists will attempt to detect gravitational waves, which are ripples in space arising from the system. This accomplishment exemplifies the significance of dedication, as it took 45 years of radio observations and unceasing data collection from various observatories to yield these findings. Thank you for your attention. Remember to like and subscribe to our channel.